This conference will now be recorded.
Hoping you can all see that.
Yes, Gary.
Great. Okay. Thank you, Jules. My name is Gary Keenor. I work for Atkins. For Atkins, I'm a group engineer. I look after the electrification discipline. My sort of project focus is in the southwest, based in Swindon, but I also have a role within Atkins, acting as a technical authority for overhead line. And as we said, I'm going to talk to you today about how we mostly solve the problem of Steventon Bridge using some unusual and groundbreaking techniques to do it. I'm going to start. I apologise to those of you on the call who are OLE engineers. There is a couple of slides just to bring everyone up to speed on how OLE performance and gradients work, so that everyone has that understanding. And then we'll talk a little bit about the dilemma of Steventon, what we did about it in terms of the modelling software that we now have, and how we approached modelling Steventon, what the challenges were. We'll talk about what the predictions were that came out of that modelling, and then how that informed the real world testing that we undertook, and what the outcome was for Steventon, but most importantly, what the outcome and the implications are for the wider electrification piece. So a couple of slides first to bring everybody up to speed on OLE performance. The thing that overhead line engineers worry about more than anything else is the dynamic behavior at the point where the pantograph meets the contact wire. And for electric trains to work well, for the system to remain undamaged, there needs to be continuous contact between the pantograph and the wire. Now, any loss of contact will result in energy loss, but also electrical arcing and some erosion of the wire due to that electrical heating. And significant loss of contact can be much worse. It can damage the pantograph or even pull down the wire. Now, the wire has to be tensioned to provide good performance, so we apply anywhere between 1 and 2 metric tons of tension depending on the system. And broadly speaking, the faster you want to go, the higher the tension needs to be. I'll show you an animation in a minute which hopefully makes that a bit clearer. Meanwhile, the pantograph itself has to be very lightweight in order to have low inertia, and you need low inertia to be able to follow the variations in the wire position. So the pantograph has 2 levels of suspension to deal with that. It has primary and secondary suspension to deal with both low frequency and high frequency movement in the wire, and I've got some video that will illustrate that shortly. So this little rather simplistic animation hopefully is going to illustrate what happens where as a train runs down, pantograph runs down the wire. So the pantograph exerts an upward force on the wire in order to remain in contact with it. This is known as the static contact force, and that is set by the pantograph pneumatic system, and we set it at a constant force between 70 and 90 newtons, so that regardless of pantograph extension, you get the same static contact force. The problem is, as soon as the train begins moving, the force takes on an aerodynamic component, which is much harder to control. And at high speeds, above around about 80 miles an hour, the aerodynamic component dominates the behavior of the pantograph. Now, good current collection is achieved with a contact force broadly between 0 newtons and 250 newtons. If we go below 0, we lose contact with the wire, and we've seen that that's bad. If we go above 250, we start increasing the wear on the wire. We go above 350, and you're getting into the zone where you run the risk of damage to the OLE. And our UK standards, because of that, our UK standards require that the mean contact force plus or minus 3 standard deviations should always be between 0 and a value that's speed dependent, but it's round about 300 newtons. So if you keep that 0 to 300 as being the sweet spot in your mind, you'll see what that looked like at Steventon later on. So this is where I've been brave here. I'm really hoping that your bandwidths all hold up and that you can make some sense of the videos that we've got in this talk. So this is a video. This is not Steventon. This is just a real world video of a pantograph as part of a test train on Great Western. And the key thing is to just get familiar with, first of all, the kind of modes of movement you see in the pantograph, and secondly, the contact force trace. So looking at the modes of movement, you can see that there's lots of very high frequency changes in position, and you can see the secondary suspension on the pan head absorbing those, and then the lower frequency movement of the wire up and down is being taken by the primary suspension, which pushes the arm up. I'll run that again. In terms of the contact force trace, so the dark blue line at the bottom is the one you want to watch. That's contact force. And the scale on the left, 0 to 300, that's your contact force scale. So you can see that, broadly speaking, and we see a little drop below 0, almost to 0 there, but broadly speaking, you can see two things. One is that the force is changing moment to moment. You cannot have a constant force because the aerodynamics and the turbulence across the roof of the train is dictating that. But the second thing is that you're staying between those two kind of safe limits of 0 and 300. And crucially, this is a very complex system. You've got the train that's moving, the pantograph that's moving, and then the OLE itself, which is also moving in response to the pantograph. So it's quite a complex system to understand, and certainly a complex system to model. Now, things get more complicated once you start to consider the realities of railway infrastructure. On an ideal railway, your contact wire would be at fixed height at every structure, and that would maintain the pantograph in the middle of its height range, provide predictable performance. However, most railways were built before electrification was even invented, and they have numerous road over rail bridges and often many level crossings as well. So at over bridges, we have no choice but to reduce the wire height. The cost of rebuilding every bridge would destroy the business case for electrification. Meanwhile, at level crossings, we have statutory minimum wire heights to meet in order to deliver electrical safety for road vehicle drivers. There is no maximum legal limit on a road vehicle in the UK. I bet you didn't know that. But most road vehicles are up to, but no higher than 5 meters. So that drives our level crossing wire height design. So I'll give you a few numbers that we'll come back to become important later on. Our normal nominal open route contact wire height is 4.7 meters above rail. At bridges, we'll go down to as low as 4.2 meters, which is not far off the roof of the train. And at level crossings, we're required to go to at least 5.8 meters. So as a result of all of that, our operating height range for the pantograph, the range of movement is almost 2 meters. Now, between the bridge locations and the level crossing locations, the wire obviously has to rise and fall. And that means it has a gradient. And since the pantograph has inertia, there's a maximum rate of rise and fall, which we have to observe. If the wire rises too fast, the pan won't be able to follow it and you'll lose contact. If it falls too fast, the pan will dig into the wire and you'll see increased wear over time. Now, clearly, the faster the train needs to go, the shallower that rate of rise and fall needs to be. And in the UK, our guiding rule is that the gradient should be no greater than 1 in 5 times line speed in miles per hour. So what does that mean? If you want to go 125 miles an hour, that means multiply it by 6. Your maximum OLE gradient should be 1 in 625. Now, it's important to note this is a rule, and like lots of other rules in the OLE domain, it's there to guarantee good performance. OLE is a rules-based discipline, like lots of railway disciplines, it's rules-based. When we're electrifying hundreds of kilometers of railway, it's an interconnected system. Doing all those calculations and performance checks from first principles would be extremely time-consuming. So instead, we operate to pre-engineered rules that speeds up production of our designs. So securing this performance without designing everything from first principles obviously means these rules need to be conservative. And that's quite an important point we'll come on to. Okay, so that's the OLE stuff out of the way. Now we'll talk about Steventon. We've seen that we need to be high at level crossings and low at bridges and maintain a maximum rate of rise and fall in between. So what happens when you can't meet all of those rules? So now let's talk about the sleepy and unremarkable village of Steventon, which is located just a little bit west of Didcot in Oxfordshire on the Great Western Main Line. It's a very nice village, quite well heeled, and it's bisected by the railway. The railway runs through the middle of it. And the roads around the village cross the railway at 3 separate points. From east to west, they are Steventon Bridge, which is road over rail, and then 2 level crossings in quick succession, Stocks Lane and Causeway. Steventon Bridge is a Grade 2 listed elliptical 3-arch brick over bridge. It was designed by Brunel. And then 399 metres away from it is Stocks Lane level crossing. Now, none of this mattered much until in 2009, DfT and Network Rail decided to electrify Great Western. And Network Rail did some early work on the route, and that clearly identified that the high wire needed at the level crossing and the low wire needed at the bridge were fundamentally incompatible. The gradient between the two would limit electric train speeds to 60 miles an hour on a route which is otherwise 125 miles an hour. Now, this would have added around about 1.5 minutes to the timetable on a project that was supposed to be speeding trains up. So a number of options were looked at. I mean, every option was looked at during the option development process, including closure of the level crossing. However, the closure of the crossing is an important access to a number of houses and businesses, and level crossing closures, as anyone who's been involved with them will tell you, is not a straightforward process, and it does not have a certain outcome. So in 2014, following a lot of preparatory work, Network Rail applied to Historic England and the local council to demolish the existing bridge and replace it with a higher one and provide a compliant gradient. And this would have restricted access to Steventon High Street for several months and clearly would have caused some significant disruption. Now, Network Rail unsurprisingly encountered a high level of resistance from the local community, and their application was rejected. And indeed, it has now been formally withdrawn. So while the development of the planning application was going on, Network Rail and Atkins had to get busy with working out how they were going to electrify the whole route. So we Atkins were the designer of the OLE through Steventon, and in fact all the way from Maidenhead through to just shy of Bristol and also down to Newbury. So we needed to undertake the design through Steventon and through the level crossing. And faced with the uncertain outcome of the planning application, Network Rail asked us to provide multiple designs at Steventon. So we did 2 main designs. One assumed that the bridge had been reconstructed with a compliant gradient, and the other assumed that the bridge remained in situ. Now, clearly the in situ design couldn't comply with the gradient rules. So we did the only thing we could do, which was to apply the shallowest gradient possible, which turned out to be 1 in 202. So remember, it should be at 1 in 625. The rules do allow us to nudge down to 1 in 500, but we were at 1 in 202. So even stretching the rules a little, this meant electric trains wouldn't be able to go faster than 60 miles an hour, according to the rules. So move forward a bit further. By 2017, entry into service is rapidly approaching, and Network Rail, the planning application is still going on, and Network Rail had to make a choice about which design to build. So practically they had no choice but to build the in situ option, complete with a steep gradient. So this diagram illustrates what that in situ design looked like, and in fact how it's been installed. So the red line is the contact wire profile, and what's notable is you can see on the far left and on the far right we have nice shallow compliant gradients, but between Stocks Lane and Steventon we have the very non-compliant gradient of 1 in 202. I hope this also illustrates and puts to bed the idea that this is an electrical clearance problem. It isn't. In actual fact, Steventon Bridge already has reduced electrical clearances. This is not a problem that could be solved by adopting smaller electrical clearances. The only way to provide a compliant gradient would be either to shut the level crossing or rebuild the bridge. So to give you an idea of the performance challenge that this gradient represents, at 125 miles an hour, the pantograph would move through its entire operating height range in about 8 seconds. And you'll see what that looks like in a few slides' time. So roll forward again on the timeline. By August 2018, it was clear that the bridge wasn't going anywhere for some time. So Network Rail then energized the OLE as installed with a non-compliant gradient, and began to discuss with GWR how to make some hard choices about how to operate this railway, which is due to come into some electric service at the end of 2018. So the outcome of that was that in October 2018, electric trains did begin running west of Steventon. However, they did not go through Steventon on electric. GWR were switching their bi-mode trains back to diesel before the bridge, and then switching back to electric the other side of the level crossing. And this is purely to keep speeds up. If we'd have dropped the speeds down to 60 miles an hour, that would have been a significant penalty. Whereas at least switching back to diesel, they could maintain something like the required timetable. Now, crucially, the bi-mode trains do not accelerate well when they're on diesel power. So this restriction was particularly affecting those westbound trains that stop at Didcot, which were then forced to accelerate from Didcot station on diesel. And by the time they got to Steventon Bridge, we're only doing 60 to 70 miles an hour. Now, GWR could just about accept this operational restriction as long as the trains are running on diesel timings, but everybody knew that in December 2019, the new electric timetable comes in, and we needed to accelerate. And at that point, this restriction would not be acceptable. So we had a real dilemma. What was to be done about this? Now, the thing we talked about rules, this one in 5 times line speed rule is just that, a rule. It's sometimes possible to break generic conservative rules at a specific location. But that requires computer modeling to simulate and understand the dynamic behavior of the system. Until recently, this simulation process for OLE was very time consuming, very expensive, and for gradient scenarios, fairly inaccurate. Only a few companies could provide the service, and Atkins wasn't one of them. But during 2016 and 2017, we had developed a new analysis tool, which we call Dynamic Rail System Simulation, DRSS for short. Now, DRSS uses a finite element analysis approach to accurately simulate the real-world conditions of the system, and it can simulate the behavior of both the wire and the pantograph. And it can provide much faster results than the traditional lump mass modeling methods that have previously been used. So this video that I'm showing you is a typical visual output from a DRSS simulation. It's really important to understand this isn't an animation, this is an actual output from a simulation. So this is showing in real time what's actually happening. The little light green patch you can see on the contact wire as the pantograph passes along it is the area zone of increased contact force. So this allows us to understand what the minimum contact forces are, maximum contact forces, what's going on moment to moment. Now, we'd used DRSS on a couple of smaller scale problems on other projects, and we publicised that a little bit. So our client on Great Western, Network Rail, were aware of the tool. And Network Rail and Atkins both shared a suspicion that Steventon could run faster than the rules would suggest. After all, we have Series 1, which is a high tension OLE system, so that should help. And we also have modern low unsprung mass pantographs on Great Western, which have very good performance. But although we all suspected it was the case, none of us could prove it. And we weren't willing to risk running a test train to find out without having some comfort first. So for that reason, towards the end of 2018, Network Rail asked Atkins whether we could model Steventon in DRSS. And the goal of the modeling would be to provide Network Rail with sufficient confidence that we could undertake physical high-speed testing without incurring risks of any untoward consequences, dewirements, or increased wear or other unpleasant results. So initially, we were asked to model probably the most pressing problem, which was the IETs, the Class A2X Hitachi trains. So we were asked to model the 2x5 car IET with 2 pans raised at a spacing of 214 meters and take that modeling up to 125 miles an hour and see what happened. So it was clear from the start that using DRSS to model Steventon would be a big step change for Atkins. It'd be the first time we'd used the tool to model excess gradients and the first time we'd modeled high speeds. So we therefore needed to build confidence that our model would be an accurate reflection of reality. But how do you do that? That your client, the network rail, want to model to inform the physical tests, but we need physical data to validate our model. It's a classic catch-22. However, while there wasn't any electric test train data for Steventon, there was plenty of data at other locations on Great Western. So the challenge there was to find a location that looked like Steventon, with a level crossing and a bridge close together and a gradient in between that had been subject to high-speed physical tests. And we found a very suitable location quite nearby, a place called Knighton, where we have a level crossing and then fairly shortly followed by an overbridge. So what we did was we took our design through Knighton, we used that to generate a DRSS infrastructure model, and we then ran the pantograph through that and compared it to what the test train data was showing, what the real world results were at Knighton. And when we did that, the results were disappointing, to say the least. There was no correlation, essentially. And so I'm going to explain why that is and what we did about it then. And to explain why, it's necessary to understand how we traditionally model pantographs in these OLE simulations. We traditionally use a simplified model. A pantograph is quite a complex arrangement. It's got a pneumatic system, springs and levers. So we simplify it as a set of idealized masses, springs and dampers, and you can see one here. We call it a lump mass model. Now these are models, they're industry agreed, they're published in a network rail standard, and they give a tolerably good simplified model that describes the pantograph behavior when you're trying to work out whether a particular pantograph will work well with a particular OLE system. However, clearly it's a hugely simplified model. It takes no account of frictional effects, hysteresis, the behavior of the pneumatic system as it responds to rising or falling wires. And this is the key reason why the initial Knighton results were so disappointing. We'd like to move away from using lump mass models and instead use a multi-body model. An FEA environment allows you to do that. But there are some IP barriers to getting to that information. So at the moment, we're using lump mass models. So how do we overcome this? Well, what we needed to do was to tune the lump mass model to more closely reflect the observed behavior as seen by our test train at Knighton. So that's what we did. We spent some time tuning the model, the pantograph model, and then rerunning it through Knighton until we were happy with the results. So let me just explain what these graphs show. So the green line, the top line, is the contact wire profile through Knighton. We start on the left at normal contact wire height, we rise up for the crossing, and then we drop down steeply to reach the overbridge. This is still a compliant gradient though. We go through the overbridge, we come back up to nominal contact wire height, and then off we go. The blue dotted trace is the actual contact wire, the contact force seen by the test train. So that's what we're trying to get to. The red solid line was our initial modeling simulation through Knighton using the standard lump mass model. Now what you can see comparing the two is that there's a clear relationship between wire height and contact force in the real data, and that's a function of the fact that the higher the pantograph is, the more it's being exposed to those aerodynamic turbulence forces. Whereas our simulation was basically showing no correlation between wire height and contact force at all. So that was no good. The yellow line is after we'd finished tuning the lump mass model to more accurately reflect the behavior we were seeing. So what we see now is that we closely follow the mean contact force. We've got good correlation with mean, but we still aren't capturing maybe all of the peaks. We're still not, it's not perfect. We're not capturing all the peaks in the contact forces. But crucially, we now had a lump mass model that we had some confidence in, and we also knew what its weaknesses were and what caveats were around it. So with Knighton now showing that our model correlated well with reality, with some known caveats, we moved back to Steventon. and we built the DRSS model of Steventon, and we ran our tune model through it. And these are the outcomes from that. Again, the green line is the wire height profile through Steventon, the bridge on the right, the level crossings on the left. The dashed line is the original model, the untuned model, and then the solid line is the tuned model. So again, we can see a clear relationship between contact force and wire height. So, having done the simulation at various speeds through Steventon, what did that simulation show us? Well, what it said is that at 60 miles an hour, we would be compliant. We would be within the UK standards for contact force. Our mean force plus or minus 3 standard deviations would be well within 0 and 300. At 85, we'd be on the edges of compliance. And at 110 miles an hour, we would see some non-compliance. But crucially, none of the non-compliance would be significant enough to risk damage to the OLE or the pantograph or other unpleasant outcomes. So this initial modelling gave the whole team and Network Rail the confidence that we could go ahead and plan some physical tests to validate the modelling and see where the real threshold was. So on the 7th and 8th of February 2019, the whole team, so that's Hitachi, Network Rail, Atkins, and the Deutsche Bahn, who are Deutsche Bahn System Technic, who were providing the instrumentation on the pantographs. We gathered at Stoke Gifford Depot with the intention of running through Steventon on electric for the first time. And the way that this works is that we conduct the tests at increasing speeds, and we have a no-go decision at the end of each run based on the data and the observations that we're seeing. And to help that, prior to the tests, Atkins set up some automated MATLAB routines based on Deutsche Bahn's. The outputs from their instrumentation are very standard. You know exactly what the data format's going to be before you get it. So that allowed us to create some routines so that we can immediately analyze the results, with the idea that by the time the train came to rest at the end of a run, we would have already analyzed the results, summarized the findings in a set of graphs, and emailed those to everybody on board the train and everybody back at shore controlling the tests. And I think I'm prepared to stick my neck out. I think for this kind of testing, that might be the first time that anyone's ever done that, to be able to analyze that data in real time. So the first day was a bit disappointing for various complicated reasons. We only ended up with a single 5-car set, which meant we only had one pantograph up. However, we were still able to do some proving runs. We did a run at 60 and then runs at 85 with one pantograph, and we were still able to correlate the data coming off of that with the DRSS model, and we were getting good correlation with the model, which is great. On the second day, we had the full 10-car set available, which was great. What was not so great was that the weather had turned against us. We had high winds the whole day, and at certain times during the testing, we had driving rain, and you're going to see what that looks like shortly. So this was going to be a really fair test. So we did the initial run at 85 miles an hour in both directions, passed without incident, and the contact forces were as expected. So we then made a go decision for 100 miles an hour. And again, we did runs in both directions. And what we saw was the forces were still compliant. So what this is starting to show now is that our modeling was slightly on the conservative side, which is kind of a good place to be with modeling. You'd rather have modeling that's a little bit conservative than going in the other direction. So this gave us enough confidence now to go for a 110 mile an hour test. And the 110 mile an hour test in both directions showed that we had contact forces on the margins of compliance. So we then had a conference call, fairly understandably a tense conference call, to work out what to do next. And so when you're doing these tests, it's often important to go beyond where you want to be in order to know where the boundary conditions really lie. So after the conference call, we did make a decision that we would go ahead and have a 125 mile an hour test. So what I'm going to show you in the next couple of videos is the actual footage from those tests. So this is footage from the instrumented pantographs on those tests. So the video is fairly short video, so I'll put it on a loop. I'll run through it a couple of times, and I'll talk you through different aspects as we run through. So the first run at 125 mile an hour was run 7. The weather conditions were very gusty, but at this point still dry. The left is the rear pan, the right is the front pan. Now, what we're seeing at the moment is we're rising towards the level crossings on a nice compliant gradient. So what you see now is a almost imperceptible lifting of the pan. That's a normal rate of rise for a pantograph. And crucially, again, remember the dark blue traces are the contact forces, and you're looking for them to stay between 0 and 300. So this is the first level crossing that we hit with the front pan, and then the second level crossing, and then the front pan comes down, and you can see the very, very rapid drop of the pantograph through the bridge compared to what you would normally expect to see. So I'm gonna let that loop back through again, and I'll talk you through the kind of the contact force trace. So again, what we see is nice between 0 and 300. The rear pan is usually the most lively one, because the rear pan is absorbing all of the waves coming back from the front pan. So as well as its own standing wave, it's having to manage that from the. So the rear pan's always more excitable than the front. So probably worth focusing on the contact force trace on the rear pan. We come up through the level crossings now. And then the rear pan begins to drop round about here, and there we go. And what we see is, you can see that little peak. That little peak there was 316 newtons. So we're going 2.5 times as fast as the rules would suggest, but we're still seeing contact forces which are within the bounds of manageability for a test train. You wouldn't want to see 316 newtons on a daily basis, but for a one-off test train, it's perfectly manageable. So I'm going to show you the second. We did, because we still had time and we had extra paths in the timetable and we still had some time left, we wanted to get as much data as we could. So we decided to do a second out and back 125 mile an hour run. However, this time, the main reason for showing you this is that the weather conditions had taken a turn for the worse, and we had not just high winds, but driving rain through as we went through. And you can actually see when we analyze the data, you can see the difference that the high winds and the rain make to the contact force. So we'll have a look. It's the same format as the previous video. I think this time have a look at the front pantograph, because what that's showing you, do not adjust your set. It's not dodgy broad bandwidth. That is what the footage looks like, and that is driving rain lashing across the face of the camera. So you can see just how bad the conditions were, and yet we still had contact forces which stayed within acceptable parameters for a one-off test train. And then we come down into Steventon Bridge. Okay, so you might think, job done, great result. We can lift the speed restriction, but unfortunately, real railways are a bit more complicated than that. We knew that we could get somewhere near 125 miles an hour with the Hitachi Class A2Xs, but there's another electric fleet that needs to run through Steventon, and unlike the A2Xs, this one hasn't got a diesel engine. The GWR Class 387s are a 110 mile an hour EMU, and the key word in the electric multiple unit part is multiple. GWR wants to run these as 12-car trains, and that means 3 pans up with a spacing of only 80 meters at 110 miles an hour, which is actually a more onerous condition than the Class A2X, which is why Network Rail weren't prepared to look at it until we got some understanding of how the IET would perform. And it's important to note, it's not permissible to have different line speeds for different electric train fleets. It's not, it's not the way the railway wants to operate. If you have too many differential line speeds, you can get driver overload, drivers make mistakes, and obviously that can have unfortunate consequences. So we were looking for a single electric line speed. So for phase 2, we went back to the modelling drawing board and we did similar modelling for the 12 car class 387. Now the 387's got a different pantograph to the A2X, and for this train we had a lot less test data, and crucially we didn't have any for a falling wire height at all. So for that reason our findings were a lot more conservative than for the A2X, and we were basically saying we don't know what's going to happen above 80 miles an hour. But because of all of the work that had gone into that point and what we'd seen from the other tests, there was a general feeling that we would be okay to run above 60. And again, we have this stepped go no go approach on the data testing. So we repeated the testing, the physical testing, in August 2019, 3 pans raised, and the performance held up at 110 miles an hour, which was great. So let's wrap all that. What was the outcome of all of that work? So as a result of all of that, Network Rail was able to raise the permanent speed restriction for electric trains to 110 miles an hour, and that took place in September 2019, just in time for the timetable change in December 2019. And this slide shows electric train running on the first day of electric service. So what this means now is that long distance trains no longer have to switch to diesel and back again. So that time penalty has been significantly reduced. And obviously that's a really positive result for the project, for the route, and for the train operator. However, it is a mitigation, it's not a complete solution. GWR still got a timetable constraint, there's still a constraint there. And Network Rail is expecting to see increased wire wear on this steeply graded section. And they're expecting to see related additional maintenance related to those higher forces. So for that reason, Network Rail are now undertaking a detailed wear measurement through the whole graded section every 6 months, and with an aim of better understanding what the wear rate is now that we've got multiple pans per hour going through the bridge. So the good news is we've used the tool to raise electric train speeds from, frankly, what would have been a crippling 60 miles an hour to a much more palatable, but still reduced 110 miles an hour. But there's still a restriction there, and to utilise the full capacity of the railway and achieve 125 miles an hour, the only way to achieve that is through a reconstruction of the bridge. So until we get there, Network Rail will need to continue implementing that extended inspection and maintenance regime at the bridge. So that's all great, and great for GWR, but actually has implications far beyond Steventon and indeed beyond Great Western. DRSS has shown that we can remove significant capital cost and program time from a major program of work. It's obvious from that DRSS opens up significant possibilities for other electrification scenarios, and I just want to talk about what some of those are, and then we'll kind of wrap this up. If we look at new electrification, it's got the potential to extend the capability of an existing OLE system that's maybe got a lower tension beyond its current stated limits. That's a possibility. Or maybe on an electrification scheme, we could use DRSS to implement a higher tension system, because clearly using higher tensions is part of the reason why Steventon works. So we could implement a higher tension locally at a difficult location and then use a cheaper, lower tension system elsewhere. But it's not just about new electrification. This has also got interesting uses on existing electrified routes. You can use DRSS to model a route and understand what's happening within the OLE pan system and why that, maybe why it's driving poor reliability, why you're getting dewirements. So it can allow you to facilitate a more targeted maintenance approach. The other thing you could do potentially with it is if you want to increase line speeds on an existing electrified route, you might be able to do that and demonstrate that you don't need to regrade the OLE. That's a possibility as well. So DRSS is genuinely a revolutionary tool. It moves us away from the traditional OLE detailed design using a rules-based approach to one where we can look at things from first principles to solve challenging locations. So in the context of the campaign to decarbonise UK rail via a rolling programme of electrification and the need to reduce unit costs, that's clearly part of the answer. And DRSS essentially has two main use cases. The first is, as we've just seen, to solve a complex problem where you need to find out where the true boundaries of performance are. But there is another use for DRSS, and that's to answer where you have a simple question and need a simple answer as to what the true behaviour is. So, and we did that actually quite recently at Cardiff Intersection Bridge on Great Western, where Network Rail needed to find out quite quickly as part of the derogation from standards, what is the actual value of uplift that the wire will see through the bridge when we start running trains. And for that work, which was a very simple, tell me the answer to this question, we undertook the whole work from a standing start, all the modelling and then reporting the results in 2 working weeks. So it just gives you a flavour of just how fast this modelling can be compared to the old approach where you would probably need to wait 3 to 6 months to get the answers. So I want to close with a message to those of you who are involved specifically in electrification schemes. Previously, you would, as designers, you would do everything necessary to comply with the rules, including, if necessary, pushing your civil and track colleagues to think about bridge reconstruction or track lowering where a bridge is constrained by a level crossing. And these rules that we operate to are like a safe haven. You're safe as long as you're within the rules, but you don't actually know where that real red line is at that specific location. So you don't know how far outside the rules you can step before you run into trouble. And DRSS offers a low cost and quick way of checking to see whether or not you can go outside the rules, and if so, how far. So, to do a typical DRSS model based on if we already had a design and we already knew what the pantograph type was, we're talking about 3 weeks to build a model, a week to do the simulation, and maybe 2 weeks to pull together the results, analyze the data and report back. So 6-week end-to-end program. So very, very easy to manage within an ordinary design program. So I'm going to wrap up now, but in closing, if you're faced with a challenging location, before you recommend a £2 million bridge reconstruction, perhaps think about commissioning some DRSS modelling and then see what life looks like outside the rules. Okay, well, thank you all for listening. I hope you've been able to follow that. I hope the video has worked for you. Before we go to Q&A, I just want to make some acknowledgements because this was not Atkins doing something brilliant on its own at all. This was a genuine piece of collaborative work. So I just want to acknowledge a few people and companies. Simon Warren from Network Rail, who is on this call. Hello, Simon. Simon was absolutely at the core of getting this all to work. Just the logistics involved in running a test train is one of the most complicated things I've ever seen to organise. So Simon deserves a huge chunk of credit for that. Peter Dearman, who really was the kind of driver behind challenging in the first place and saying, I think we can go faster at Steventon. It's really down to Peter that process even started. Dr. Nikos Bypass is the very, very smart chap who actually undertook the modelling and understanding what all the data meant. Couldn't have done it without Nikos. And then DBST, who ran the instrumentation, who were incredibly cooperative in allowing us to understand what the outputs would look like. Hitachi for pulling together, taking 2 trains out from normal traffic and having them covered in wires and widgets is quite a thing. And then obviously Great Western Railways for doing the same. So that's it for me. Thank you for listening. And we'll go over to Q&A now.